Yeah, welcome to Cryptography on Hardware. My face might be new to many of you. I'm Amir Moradi and pretty new into Darmstadt since last year, October. I'm in the Fachbereich Informatik. And this lecture, Cryptography on Hardware, is somehow dedicated to the schemes and the methods that we should provide or we should implement cryptographic primitives on hardware platforms. Now, hardware platforms you may have heard, like FPGA, ASIC, and something like this. That might be very far from what you have learned. I don't know. Might be very easy for you, might be a bit hard. Let's see. Good. Then we start with the cryptography on hardware and see whether it's interesting for you. I guess most of you are already registered in the Moodle course, and I will try to put the slides in the Moodle before the lecture. Means that on Monday of the start of the week, when we have the lecture, on the Monday, I hope I can provide the slides ready for you. And then after the lecture, I will also try to upload the video of the presentation and also my face, if you like, into the Moodle course again. If by any chance you could not attend, then you have some information and some resources to learn. At the same time, there is a Zoom link, which is also provided in the Moodle course. If again, by any chance you don't want to come or you cannot come, then you have this chance also to join. Now, something about the motivation, why hardware and mainly FPGAs. I will explain why we are actually concentrating on FPGAs here. Beforehand, who is not familiar with FPGA? Who is familiar with FPGA? Okay. Means that you have already programmed something on FPGA and checked, and practically you have some experience, right? That's good. Then you know what the FPGAs are, but I will explain here. Of course, what I explain here in the lecture is not dedicated to FPGAs, mostly. Some parts are dedicated to FPGA, but mostly it's not FPGA based. It's generally about hardware, means that we write HDL, hardware description language, codes, and it can be run on or can run on FPGA or ASIC. It can be ASIC design. But of course, for the exercises and so on, we will use FPGAs. Something about the motivation, why we select hardware compared to software. Software, if I talk about software, I don't mean, for example, your PC, which is a super large and CISC processor. We are not talking about, for example, Intel or AMD or something similar CPUs. We are talking about, for example, embedded CPUs like the ARM processor, like RISC-V and so on. And of course, here, software for me, as I said, means the microcontroller, and hardware for me means FPGA or ASIC. And here at the hardware side, you have high efficiency, means that you can design or you can implement cryptographic primitive or generally some functionality with very high efficiency, means that with high throughput, very fast compared to software. Software, usually you have sequential operations. And then when the functionality that you want to implement is heavy, then you need many clock cycles to accomplish a particular function. And then this can be done in hardware pretty fast, for example, by some parallel processings. The bad side of hardware, if you are an ASIC side, it's completely fixed. Means that when you design the hardware or circuit, it's fixed. You cannot change it afterwards. Of course, if it's FPGA, you can. But then in the software, you have full flexibility. You can change the program at any time that you want. And then in the software, the challenge is the code size usually. And of course, as I said, the number of clock cycles. And the program should fit in the code size and the memory that you have. But in the hardware, the point that you have is the area. For example, how much area you can spend on your design, how many gates you can put in your design. Because the FPGA resources is restricted for sure. You cannot say I select an FPGA which is as large as I want. Of course, it will be more expensive if it's super large, and then it might be not available in your application that you want to implement the crypto. And of course, we selected the hardware because of the efficiency, and then after, of course, speed is important for us. Yeah, it means that we want to implement something with higher speed. And as I said, yeah, we have parallel operation here, the hardware side, and sequential operations in the software side. Yeah? These are mainly the things that I already explained. Yeah, implementations are limited through the required memory in the software, program memory and data memory. And just as a note, you may already learn there are two types of the memory, yeah, volatile memory and non-volatile memory. This is just a recap of what you probably have learned during your bachelor. Yeah, volatile memory means the RAM or even the RAM of your computer, your PC. When the power is off, the data which is stored or was stored in the RAM is gone. Yeah, the same in the microcontroller. When there is a RAM, yeah, when the microcontroller is restarted, everything which was in the RAM is gone. And non-volatile memory or NVM, there are different types. Yeah, the ROM, PROM, EPROM, erasable PROM, electrically erasable ROM, and also the flash memories. Yeah, it means that when you write into this memory and then the power is gone or power is off, then afterwards, after power on, the data which you are stored in the memory stays valid. Now, and I have to explain that most of the FPGAs that we are dealing with, yeah, they are SRAM based FPGAs. SRAM means that they are RAM. Yeah. And then that means that a static RAM, yeah, means that every time that the FPGA powers up, then every configuration, everything which is in the memory of the RAM, in the configuration memory of the FPGA, everything is gone, and the FPGA should be reconfigured after every power up. Yeah, they are SRAM-based FPGAs. There are a few flash-based FPGAs that we are not working with in this lecture. And they are mainly for military applications. Means that the FPGA configuration is inside the FPGA and it doesn't need to be reconfigured after the power up. No? And the program memory it doesn't matter of microcontroller or anything else, usually is non-volatile memory. For example, you write the program of your microcontroller into NVM, non-volatile memory, which is usually at the moment the flash is the current technology. Yeah, you write in the flash memory. And then, of course, when the power of the board is gone or FPGA or the circuit is gone, then the data stays there. You know? And the microcontroller, when you write the program memory, you write in the flash inside the program, inside the microcontroller, or even sometimes outside. And the same actually applies to FPGAs. Yeah, this is the FPGA. And as I said, there is SRAM inside, which is configurable, but it's actually volatile memory. And then outside of the FPGA should be a flash or something else that during the power up configures the SRAM at every power up. Yeah, that should be configured. And then this is, of course, non-volatile memory. Yeah. Good. Now, again, a bit of motivation why we select hardware. As I said, for the efficiency, yeah, for the speed, because we want to implement the things much faster than the microcontroller or software, and the cost versus performance. Yeah. This is something that we should consider, because usually the hardware, if you go for FPGA is more expensive compared to a microcontroller. But if you build an ASIC, if you produce many chips of the same design, for example, you want to produce something and then 10,000 chips you want to produce, and it's much cheaper to fabricate a chip instead of buying 10,000 microcontrollers. Yeah? And then you pay less, for large number of productions, and then performance is also higher. And then the power consumption of these devices is usually also lower, compared to microcontroller implementations. Of course, you should compare devices with the same technology. I mean, the new technology and the new microcontrollers, which are produced with a super tiny nanometer technologies, they consume, of course, less energy compared to another FPGA or ASIC, which is produced or which was produced with a larger technology. Yeah, I mean, the comparison should be fair. And another point that we also consider here in the lecture is Security, if you build an ASIC, it's more resistant against manipulation. Means that you can easily change the program which is running on a microcontroller compared to if you have built a chip and then it's an ASIC, and then of course more manipulation or changing anything on the chip is much harder compared to changing something in the memory of the program or program memory of the microcontroller. And then you have, of course, higher security. The data is more protected because reading the RAM or dumping the memory of the microcontroller is probably easier than dumping the memory of a custom chip. And there is another point that is related to another lecture that I give in winter semesters. Yeah, side channel attacks or side channel analysis attacks. If you find this interesting, I mean, you may join or you may see the lecture that I give in the winter term, which is called Physical Attacks and Countermeasures. These attacks are actually performed on the devices. You know, it means that if you have, some of you are actually familiar with the cryptographic primitives like the AES, you know, and if as a standard algorithm for symmetric cryptography. And then if you implement, for example, the AES on a hardware or software in microcontroller or ASIC or FPGA, and then you think, okay, AES is secure and I implemented an AES on my device, but it's possible to recover the key which is stored in the device using power consumption of the device. It means that we measure power consumption of the device and then we try to get some information about the key which is stored inside or is processed by the processor or by the FPGA or by the ASIC. You know, this is called side channel analysis attacks. And here in the hardware side we have more options. We have more option to, sorry, we have, the pointer doesn't work. We have more options to provide side channel security. And there are some special functionalities that they are only available in hardware, not in software. For example, if you have heard about PUF, which is physically unclonable function, yeah, means that you want to produce one chip and then one particular design you have for this chip, even if you reproduce the same, exact the same design, you produce just another device, as two devices or two chips or two FPGAs, they are exactly the same design is running on them, but they have different functionalities. Yeah, means that you make somehow a fingerprint of the chip, means that you can identify this is this chip, this is another chip if you communicate with them. And this is called PUF, or physically unclonable function. Means that if you even fully copy or clone the design of the microcontroller or ASIC or FPGA, then not the same functionality you can get if you actually copy it or clone it. I mean, the functionality of these two copies will be different. This is very easy to be implemented on hardware, and it's a bit harder in software. This is another motivation to use hardware for these purposes. And of course, building TRNG, which is true random number generator, there are a lot of options and facilities to build TRNG inside the hardware chip, compared to software. I mean, of course, there is a PRNG, pseudo random number generator, which is, I mean, if you study IT security, you should know that randomness is highly required for many different applications of security. And then sometimes, many times you have to, for different protocols, for different primitives, you have to select one random data and then perform some operations. And then the source of randomness is super important. If you have very weak source of randomness, then it's not guaranteed that everything works correctly. Then the hardware provides these options for you to build TRNG and PRNGs. What it is, or what are our goals in this lecture is to give you some information what is hardware. I mean, I believe you already learned something during your bachelor, for example, in digital technique. It says digital circuit design, about what the hardware is, how we can, for example, write some VHDL code or some Verilog code. I guess most of you learned Verilog during the bachelor. In this lecture, you learn VHDL, which is not far away from Verilog. I mean, the concept is the same, just the context is different. I mean, this gives you another option or opportunity to learn another hardware description language, VHDL. Of course, I could select just the Verilog for the lecture, but I mean, then you don't learn a new language. Yeah, I mean, if you then in the future you go to industry, some of you of course go, yeah, and then you can tell that, okay, I know Verilog, I also know VHDL. Yeah, this gives you this option. And then what is crypto? Most of you already learned about symmetric cryptography, asymmetric cryptography, hash functions, POF and PRNG and TRNGs. We may have some introduction about them because we need to implement them. I mean, in this lecture we learn, or you learn, how to implement them. And of course with several examples and several assignments. And I said, yeah, for the speed, for the area, and for the latency. The assignments are like this, that every week you get an assignment, usually every week. And then what you should do, you should write VHDL code. You know? And then how you can check them, we will give you this board. Each of you will receive one of these boards. You can keep it till end of the semester. Of course, if you stop visiting the lecture and saying that I don't have any interest anymore, you have to bring this back. You know? And I mean, the board doesn't cost much. I mean, this is roughly 100 euros. If you want to buy one for yourself, I mean, this is doable. And this is a board. I mean, we will have more information about the board, but this is an RTX 7 FPGA. This is a family of Xilinx, or let's say AMD FPGAs, which is inside here. I mean, this is the FPGA, and this is the board. I mean, have you ever heard about breadboard in some labs you have used? This is developed actually for breadboard. Means that you can put it in a breadboard, and in some wires you can do whatever you want. Yeah? And it doesn't have many switch buttons or push buttons or nothing. Yeah, I mean, it has one or two, and not much LED or something to show you something. Yeah, means that because it's developed for the for breadboard. But we are not actually interested in the lecture for example, pressing a button and then turning one LED on and off. You know, we are interested in, for example, sending the plain text to this device and then performing the encryption and sending ciphertext back. You know, this is what we want to learn. Or, for example, if it's a POF, physically unclonable function, you want a fingerprint, then you send some challenge or one challenge to the POF, and then you receive the response back. And then we should see it if you have a single design and then running on different FPGAs that you have, you should receive different results. Yeah, this is controlled by a micro USB port, which is connected to here. I mean, we give you also the micro USB port. And then what is important, you need to install a program, a software tool for that, which is called Vivado. You know? The Vivado is the program or tool chain from Xilinx. I mean, Xilinx is now as AMD. AMD bought Xilinx. Still, if you go for xilinx.com, you reach the website. I mean, because it's kind of AMD. But you see AMD logo everywhere because AMD bought Xilinx. You know? You need to make an account on the Xilinx website or webpage to install or download the program. I have to warn you that the package is pretty large. Yeah, a couple of gigabytes. And then you also you need a license to run the program, and the license is also freely given by the Xilinx webpage as Webpack. Yeah, it means that you have to create an account and then go there and then ask for a license, which is automatically generated and then gives you a file, and then you can, I mean, everything is documented, everything you can easily install and run it. I mean, if you don't have a license, it runs, but it doesn't, for example, provide or generates bitstream for you. And the bitstream you need, I mean, I will explain what the bitstream is. Bitstream is actually the configuration that you put in the FPGA. Yeah? And then if you don't have a license, the bitstream is not generated. And bitstream is exactly this guy that I said. Yeah? Bitstream goes to here. Yeah? And then afterwards, after the power up, this flash configures the FPGA with the bitstream. Yeah? Good. Now, the material of the lecture, I mean, you know, you have slides and the videos and some books and the papers, you know, if you're interested. And then there will be an exam, a written exam, 100%, means that you need to get 50% at least for the final exam to pass the course. and 10% bonus as the exercises you get. I mean, if you do exercises, which I strongly recommend you, because you learn exactly this lecture by doing the assignments and exercises. If you say, I don't want to do assignments, I warn you that most likely you will not pass the exam. I mean, not based on the grades that you get, based on the experience that you learn. Good, there are some literature, if you are interested in learning again of reviewing digital design, like digital technique. I mean, something like Maurice Mano I can recommend. I mean, this is not very recent, but this is the concept, which is already 5th edition, 2013. And there is something about understanding cryptography. If you have not studied IT security, and you don't know, for example, what AES is, or symmetric crypto is, or asymmetric crypto is, or hash function is, then I would recommend you this book, Understanding Cryptography. And for VHDL, there is a golden reference guide from Dolos. And there is also, if you want, there is a free range VHDL, which is also a book here that you can get it from this link. Good. Now, any question? Organizational question before we dive into some technical part of the lecture today?
What kind of will the exam contain some kind of programming task, or will it be more transfer-like?
There would be most of the time in the exams, most of the questions will be conceptual questions, to check whether you really understood the concept. And there will be something about the context of the VHDL, some part of the code that you should provide knowledge that, okay, for example, you know where to put the semicolon, how to assign some signal to another signal, for example, finding some error in the VHDL code, that one 2-bit vector is assigned to another 60-bit vector and something like this.
Yep. Do we need a recent Vivado version, or the version?
Usually every version that you have should support this RTX7 FPGA. The new versions of the Vivado, which is the latest version that I have currently here, I mean, I can show you. This is running here, This is the Vivado. Vivado. And then, of course, we will have a lecture about this. The version that I have is 2023.2, and I think it's not the latest version, as far as I know. And this supports directly the FPGA that we want. It's not a problem. For example, this is the VHDL code that we will deal with this today as well. It doesn't need to be the latest version. I mean, because what is important, you have to, I guess, here, settings. This is still thinking, because my PC is doing a lot of things at the moment. And then here, project device, you can select which FPGA you have. And then you see this is a RTX 7, XC7A. This is one of the RTX 7, but you can select here family, for example, RTX 7, and then the package. I mean, these are given already in the board. I mean, I did not tell you what the board is. Sorry for that. Here, the board is called actually CMOD A7. CMOD A7 is the name of the board. And as I said, it's produced by Digilent, and Digilent is an American company which produces some devices or some toolkit boards. But then this information about which package it has, I mean, you can get all information in this link. But then what I want to say that even the super old versions of the Vivado support RTX 7 FPGAs, because they are not new FPGAs. Good. Any other questions? Okay. Now, today we see just 20 slides roughly about technical part, about a bit review of what you have learned during digital technique or digital circuit design, that there are different ways to represent logical circuits. When when building a circuit, we finally need to make a netlist of fundamental cells. Yeah. This is, for example, I mean, you define functionality, and then finally, the result of building a circuit will be something like this. Yeah, it means that at the end, we want to build a circuit using some fundamental gates by AND, OR, XOR, NOR, registers, means flip-flop, and so on. Yeah? The combination of these things will build a circuit for us. In ASIC, each of them inside the library that you have, because for every ASIC design that you want to put or you build or fabricate, you have to select the library. Now, and then inside the library, these are defined how they are, and the shape of the AND gate, how the transistors are connected together to build an AND gate. Yeah? This is the ASIC design. And then you need to really geometrically put this together, I mean, not manually, with some tools to build the circuit. In FPGAs, then instead of these things, instead of this AND and or something like this, I don't know why the pointer doesn't work correctly. I don't know what happened. In FPGAs, we will see later, but these will be implemented by some lookup tables. Yeah? And then how they are connected together, there are some programmable switches that they connect different wires to different coming signal to different destinations. It can be configured, and this makes really the configurable hardware. It means that the lookup tables you can configure, and the switching matrices you can also configure, and then it allows you to build the circuit in any topology that you want. Yeah, these are already explained. The library of the implementation platform is important. How do you build this? Yeah, in some libraries you have three input AND gate. In some other libraries you don't have. Yeah, just 2 input gates available. Yeah. Now, for example, here, now we can say, hey, if I want to write down this circuit, hey, I have a bar, I just call it AP, not of A, and BC is the AND of B and C. And here I have a NOR, which is the NOR between AP and BC, you know? And then another AND gate, which is 3-bit AND gate, with D, which I call it here D, and A, which is coming from here, and B is coming from. And this is a representation of the entire circuit that you have. Yeah? I mean, I guess you learn already in Verilog or any other language that you can write this as a netlist, and this is a netlist representing the circuit that you want to implement. Yeah, if you don't have, for example, 3-input AND gate, yeah, here you need to actually change this, yeah, and say I have just another signal, which is E, AND between A and B, and another AND gate which gets this and AND it with D, and then you have the same functionality because you don't have 3-bit AND gate. Yeah, that looks simple for small circuits, and if you want to build larger circuits, you cannot do it by hand. You know? I mean, you learn probably Carnot table, you know, and some other sort facilities or schemes to simplify functionality and then optimize one functionality or presentation of the function. But then if the circuit becomes large, it takes an ages to do this by hand, and then also write everything by hand in a netlist level. Then HDL, Verilog, and VHDL will help you to write the functionality of the function in a behavioral level. And then the synthesizers will understand this and translate this for you to a netlist using the library that you define. You know? I mean, library define, I have which kind of AND gates, I have which kind of OR gates, and which elements or components are available in my library. And of course, you can also simulate this with some tools. I mean, Vivado, for example, gives you this option to simulate as well. I mean, you write the behavior level code in Verilog or VHDL, and then it can also simulate for you. You can synthesize it, build a netlist, and then afterwards also simulate the circuit. You know? At every level of abstraction, you can do the simulation. Yeah. You know about the, again, something what you already probably have learned about the HDLs, or hardware description language. Now, the VHDL is very high speed integrated circuit hardware description language. Of course, we just saw it VHDL, and you also learn about Verilog, mainly in the US, is used by companies. But I have to say that every company is different. Some companies prefer VHDL, some other companies prefer Verilog. Yeah, it depends. And there are some other languages like UDL, mainly in Japan and Asia, and there are older languages like ADA and so on. Yeah. This is what you already know, that the HDLs allow to program or write a description of the functionality of the function or what you want to implement, similar to writing a software. But of course, there is a conceptual difference between them. In software, you have sequential operations. In hardware, you don't have these sequential operations. Good. Yeah, we must stay with the hardware conditions, means that there are some conditions when you want to write the hardware or HDL code. Yeah, for example, it's possible to write some HDLs that can be simulated, but they can never be mapped or can be constructed using any hardware or FPGA. Yeah, some of these codes are not synthesizable, we say. They are simulatable, but not synthesizable. And this happens usually in VHDL, not in Verilog, but there are available also things in Verilog that you can write, that they are simulatable, but not synthesizable. But this happens more often in VHDL because VHDL is, I would say, a higher abstraction level usually. Yeah, there are some functionalities in the VHDL that they are pretty hard to implement in Verilog, and there are also other way around. Yeah, there are super simple things that you can write in Verilog that you can hardly write in VHDL. Yeah, each of them has some pros and cons. A bit history of VHDL, you may know, but it's the first discussion about the VHDL was in 1980 that, okay, we need such a language. It took, of course, 13, 12 years till the first version was developed, which was almost 30 years ago. The version that you are dealing with is almost 30 years old. Of course, there was a couple of updates during the 30 years. But the main concept is the same, yeah. What is available in VHDL and what is supported. Good. To understand the HDL, we should first understand the difference between software and hardware. I just give you an example. Again, as I said, if you have passed digital circuit or digital technique, very good, then you should remember this. Otherwise, it may have happened that you just passed the course when you were in the first or second semester, and then afterwards you never touched Verilog at all. And might be very well known to you, but for example, if you have in software, your software, you write something like this in C. Yeah, this is my favorite language. If you don't know C, I guess you know. But you just define some vectors with A and B, each of them 5 elements, and each of them also an integer. It depends on the compiler, if it's 8-bit, 16-bit, or 32-bit. It doesn't matter. And then you just write a loop from 0 to 4 that C, every element of the C is just the result of the addition between the corresponding A and B. Yeah? You know that 5 clock cycles, for example, it should take. If every addition takes 1 clock cycle, which is usually not the case. Yeah? If you have a microcontroller, usually this addition may take longer, yeah, than 1 clock cycle. Depends on the architecture of the microcontroller. If you look at super old microcontrollers like 8051, every of this addition takes 12 clock cycles. If you look at the ARM processors now, because of the parallel processing and pipelining, then roughly in average, you can say every addition takes, for example, 1 or 2 clock cycles. Yeah. Now, this is what we discussed, a couple of cycles. But if you write it in hardware, this is one VHDL code. No panic. We will discuss about the details of the VHDL later. Yeah, we defined as the entity, and we just give it a name and a port ABC, and there are 2 inputs, each of them with 5 elements, and each element is integer vector. or integer, and then C is the output, and the output is also 5 elements, and each of them is also an integer. And then here that we define the architecture, and we just write that C0 is as A0 plus B0, and C1 is A1, B1, and so on. Of course, you can write a loop here, yeah, generate loop, we will learn later. And then what happens in hardware, this is actually the, again, as I said, this is the netlist or the functionality of the hardware. It means that these additions are performed at the same time together in parallel. Yeah? Means that, I mean, you can imagine that, okay, one clock cycle is initialization, second clock cycle is just doing the addition, and the third clock cycle is end. Is actually not similar like this. This function doesn't have any cycle. Yeah? It doesn't have any clock. Yeah? It's just a combinational circuit, just without any flip-flop, without any register. Yeah? Nothing. It's just a lot of combinational logic like AND, XOR, OR, NOR, inverter, and so on to build these additions. I guess you learned already the addera, yeah, how we can implement the adder in hardware. If you remember, if you don't remember, I can give you some names like Cary-Luke adder or Kogan-Stone adder, if the names are familiar with you. Yeah, I mean, but now in hardware, I have to say that in hardware at the moment, what you do, you just the addition. And then the synthesizer will use some libraries that it has to build this adder. Yeah, to build this adder, and of course it will try to do the best adder depending on the synthesizer. Yeah? I mean, how good is the synthesizer? And then everything will be just a combinational circuit, and these additions are performed exactly at the same time at once. Good. Now, another example, entity and architecture of an example for comparator. You know comparator, right? You want to check whether one value is larger than the other. Yeah, just we imagine here that we have entity. Yeah, this you have to keep. Yeah, and the name compare. This is the arbitrary name that you select. You say entity blah blah is, and then you select generic. Generic is actually the parameters that you have, the constant that you want to use. For example, you want to write a compare module which works for every number of bits, not only for 4-bit values. Then if you want to use another 8-bit comparator, then you need to build another comparator for the 8-bit. Then here you can make it generic, or you can make it parameterized and define n as a positive value, which is by default 4. It means that if you do not define the n, then it will be 4. And then you define a and b as 2 inputs, each of them bit vector from n-1 down to 0. Yeah? And then one output value as b, here output saying that a is larger than b or other way around. Yep.
Was the slide before, like in Verilog, we have like always clocks, and if you want to have something change on the clock edge, you write always on clock, blah blah. And is that like combinatorial logic, or is that implicitly clock?
Combinatory.
Okay.
Fully combinatory, because there is no clock. And in Verilog, if you want to write, this is with assign. Yeah, you just write assign, for example, C0 equals A0 plus B0. Yeah? The always block, what you say in the Verilog, is something similar in VHDL. They are process. We will learn this later. Yeah?
The arrow assign is not as Verilog a blocking assign.
Error assign or error?
The assign like C.
The assign that I wrote.
It's not the blocking like Verilog. It's just the
Blocking. Blocking, non-blocking things are just in the process, not if you just write assign. Yeah, I mean, this way you probably mean this guy, which is not here like this. This is just in the always statement in the Verilog. In VHDL, this is something that is called process that we will learn later. But assign is because there is no process, there is no blocking, non-blocking, because there is no clock. Now, I mean, we were here that you have a parameter, and then there's some ports as input and output. And here, this is the process. This is what I said, always. Yeah, and the process here says it is sensitive to A and B. If A and B, any of them changes, then this process works or is active. And you say if A is larger than B, result is 1, otherwise result is 0. And you should keep in your mind, this is not something which is done sequentially. This is just a way to write the functionality of a hardware. And the synthesizer will understand this and will turn this to combinational circuit. This is super important. You should not think that, okay, this is checked if, and the next clock cycle this, and the next clock cycle this, and then this is done. There is no cycle at all. There is no clock cycle here. This is just the way of representing the functionality of the hardware. Good. These are the things. I mean, ports, arbitrary name for the architecture. This we will deal with this later. You can see here the architecture behavioral one. This is just the arbitrary name. You can also define different architectures for one entity. Yeah, but doesn't matter at the moment. Just one. We want to deal with just only one architecture. The data types that we have, there are bit vector, std logic means that a standard logic, a std logic vector, signed, unsigned, integer, positive, real, and something else. We usually deal with these two, std logic and a std logic vector, because they are standard logic values. Of course, we may deal with the signed, unsigned, with the integer, and so on. But then you should keep in your mind that a std or a standard logic or each element of the standard logic vector means that a standard logic vector is exactly the same as a std logic, but with larger than one element. This means that a std logic is single bit, and a std logic vector is exactly the same as single bit but more bits. Many single bits, more than one. And then this is the logical 0. You should put it like this. And logical 1. And if you have a vector, then it should be in double quotation or something like this. And then this is binary. And if you want to represent a hexadecimal, you have to put x before. Again, means that each of them is a 4-bit. And then Z, means high impedance. I don't know whether you have learned this. Z high impedance means that this pin is not connected to anywhere. But keep in your mind that Z and X, which is unknown, and U uninitialized, they are just for simulation. In reality, when the circuit powers up, you have never something like Z or X or U. Is it logical 0 or logical value? Logical 0, logical 1 or logical 0. Of course, there are some more advanced things like open collector gates that we are not dealing with in this lecture, that they have Z, means that high impedance. They are not connected to anywhere, but we are not dealing with them in the lecture. Just keep in your mind, we are having this, but when you simulate a circuit at the power up, it doesn't know what this value or what is the value inside the register. Because after the power up, the register values are completely unknown. It's either 0 or 1. You cannot predict this. And then the simulator usually puts X. Say, I don't know what is in the register. And then you should, when you simulate a circuit, you should make sure that, for example, you reset every register at the start of the simulation, that this X doesn't happen. Good. Again, basic elements of the VHDL. You have entity, you have port, and you have architecture. These are what we have set. You have entity and the name, arbitrary name. For the port, the name of the port, and the direction, whether in or out. This is in, out. There are some also versions in, out. We are not mainly working with them in, out, only with in and out. And the type of this, and then semicolon, and the next port. And all of this, again, name of the port, direction, and the type, semicolon, and again, next one. And the last one doesn't have the semicolon. But you will learn this by some examples for sure. And then again, end of the name of the entity that you set. And then the architecture, again, any name for the architecture that you want of entity. What is the entity? This name. If you put here, for example, function 1, you have to put here function 1 because you want to define the architecture, one architecture for function 1. And then between the architecture, of is between the architecture and begin and end. Between them, there is a header of the architecture. You define the signals, wires, internal wires. They are not the primary input-output. Yeah? Because here, what you define here, they are the primary input and primary output of the entity or the module. Any other wire or signals that you want to define should be defined between the architecture and the begin. And here, between begin and end, is the body of the architecture. Good. Yeah, this is, for example, one adira or adder. That here you have some examples now. I mean, the entity adira, input A, input B, and it is input a steady logic vector. Usually we write it like this: 31 down to 0, not 0 to 31. Why? Because when you look at the vector, it will be similar exactly what you see something in a microcontroller or something in a memory that you read. Yeah, LSB here and the MSB here. Yeah, easy for you. Then usually we write it like this. And the same for the out. We define one more bit. If you look at here, 0 to 32 instead of 31. And then, for example, we want to add these two values and put it in the output. Why one bit more? Because the result of 32-bit plus 32-bit will be 1 bit more. Yeah, and it's a carry out. Good. Again, there are some just context of the VHDL. You can define here between the architecture and begin. This is what I said here, the header of the architecture and the wires. There you can select, define signal. You can say signal, define components, define constants, or define even some different types. Yeah, for example, not only a steady logic, you can define something else, an array of something that you want to build. And for example, here is a constant, the name, the constant, and the type of the constant, and then here double point and then equal to the value of the constant. Yeah, the name, again, type, you define a type, you say what is it, this type, and then you define some signals of this type, yeah, of this name type. You will see one example here. This is what you have seen already. You say constant fixed value is a steady logic vector, 3 down to 0, 4 bits, and it equals like this. Yeah, it means that this fixed value or fixed vert is always like this, and you cannot change it in the program. And then you define an array. You say my array, or it's one type, is an array of 0 to 3 of a steady logic vector 2 down to 0. It means that it has 4 elements, the array, and each element is a 3-bit vector. Each element. And then you define one signal and say, hey, my signal is a steady logic vector 31 down to 0. This is a normal intermediate value of a signal. Or you select or define a signal, say x is of my array. Yeah, means that x now is an array from 0 to 3, and each element of the array is a steady logic vector of 3 bits. Now, we will see this with examples, but you need to learn the process, which is similar to always in Verilog. Declaration of a sequential section. As I said, you may think if it doesn't have any clock, it's just a representation of the functionality of the hardware. If it has a clock, it's exactly the sequential operations which happens every clock cycle in the process, yeah, or always in the Verilog. Then you have also conditions. If some conditions, then some operations, which usually you should write this if, then, else inside the process. You cannot just write if or something, if then, or if then else outside of the process. This should be inside the process. And then what you can also write outside of the process is the conditional assignments. Means that you say one signal equals to something when some condition else other condition. What I can write for you as an example here is that, for example, you say A is like this, yeah, like B when D, for example, equals 1, else C. Yeah? It means that B, or let's say A has the value has the value of B, yeah, when the condition like this happens, and otherwise a C. It's actually what this is actually similar to a multiplexer, to say I have B, yeah, as input, or I have C, and the output is A, and the condition is D. But then we say when D equals 1, B should be the output, then here is 1, here is 0. Yeah? This is exactly the representation, yeah, this representation of this multiplexer. Good. And then there are some other things like the generate that we will see later. You can instantiate different modules in a for loop, similar to this 5 additions that I have written in one VHDL file. That, as I said, you can write loop there, but either inside a process, or you should actually do it inside a generate loop, yeah? Or generate for generate loop. This we will learn later. The same for the conditional generate or assignment or instantiation or something. Again, based on some conditions. And these conditions for the for and for the if generate, they are not the conditions that they are based on signals or some variables that they change. These conditions are usually based on some parameters. Yeah? For example, here, there is a here generic, yeah? And this is the constant value actually that you can give from outside. When you instantiate this compare module, you can say what should be the n. Means that you write this once, and you can instantiate this function or this module with n equals 4, with n equals 6, with n equals 8, and as many times as you want with different number of n, you know, with different parameter. And based on this n, you can select inside what to do. How? Based on for loop, for generate, or based on the if generate. You know? Then means that this generate for the for and for the if, yeah, they are usually based on some parameters which are constant. You know, they cannot be based on, a condition cannot be based on the signals that they change during the runtime of the device. But as I said, these things you will learn by doing, yeah, and by some examples you will learn. Again, one example, super simple example, again from first or second semester of your bachelor, by Carnot map or Carnot diagram. You have here one function here, the true table. A, B, C, D are 4 inputs, and X is the output. Of course, 2 to the 4 means that 16 different cases you have for the input, from 0, 0, 0, 0 to 1, 1, 1, 1. You know, this is the output of the function. And then you put it in the Carnot diagram and then try to simplify the things and optimize by the sum of products, for example, here. You know, I guess you remember BD plus A bar C plus A C bar D bar, you know, based on this circles that you draw. Now, this is something that you do by hand, and then you can afterwards write the VHDL for that. You know? Then what is important here, you have to always write the library IEEE, use IEEE as standard logic. This is what we use for the STD logic. Yeah, these definitions. Means that this is usually fixed at the start of every VHDL file. And then we define the entity function is, this is the port, and A, B, C, D are the 4 inputs, and output is just X. Each of them is a single bit. And then we define architecture Carnot of X function is, begin, what we wrote here easily, X is B and C, which you see here, or not of A and C, which is here, and so on. Now, this is one way you should write, or you can write. Keep in your mind that, again, since you have written Verilog before, you know that the Verilog is case sensitive. If you write large A and a small a, they are different. In Verilog, in VHDL, all of them are the same. You know? VHDL is not case sensitive. I mean, it doesn't matter if you write here this of large or a small, and even if this Carnot, you write a small or large. You know? then you cannot have large A and capital A and not capital A as two different variables, something that you can have in Verilog. And another way to write this is just lookup table. Then the synthesizer will do it for you. It means that you just write a process. And then I just define A, B, C, D as a vector of 4 bits. Vector of 4 bits instead of just defining each of them individually. And then I write here the lookup table. Let's say if B, C, D, B, A, all of them are 0, then the output is 0. Else if D, C, B, A equals 0, 0, 0, 1, then the output is this and so on. I mean, all 16 cases I have to write down here. As I said, this if should be inside the process. Should be inside, similar to always a statement in Verilog. But you may say, this DCBA, I don't want 4 bits. I want exactly like this. I want to have 4 inputs individually. Then you can write it like this, that A, B, C, D are here. And then you define a signal DCBA, or anything else, as a steady logic vector. And then you concatenate this A, B, C, D and put it in this and the same lookup table that you have seen. Concatenation in VHDL are by this. In Verilog, what you had? Anybody remembers? Verilog? Yeah. For example, you say assign DCBA equals what? Like this. D, C, comma, B, comma, A, like this. No? This was the concatenation in Verilog. Now you need to put AND here. Good. The same you can do with the case statement. Again, inside the process, you write a case. DCBA is when blah, 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 when 0, 0, 0, when this DC, what should be done? X equals blah. Of course, you can have here begin and end and write more instructions or operations. Again, as I said, this is not a sequential program. This is just a way to represent the functionality of the hardware, and the synthesizer will build one combinational circuit out of this representation that you have here. Means that instead of doing this by hand, by Carnot diagram, the synthesizer is actually, this is the job of the synthesizer. And the synthesizers usually do a good job when the number of inputs of the function is small, for example, 4-bit or 5-bit. If it gets to 8-bit, then it will be much, much larger, and the synthesizer will not do exactly, it will not do a good job usually. This is fundamentally hard to optimize a circuit with larger inputs larger than, for example, 6-bit. And then if the function is larger or has a larger number of inputs, then most of the time it makes sense to manually optimize it by yourself. For example, again, some of you have learned the AES as a symmetric cipher. The AES box is an 8-bit to 8-bit function. And if you just write a lookup table and give it to synthesizer, it would be extremely large instead of manually optimizing it by yourself, of course, through particular fashion and schemes and tricks. Good. What is a synthesis? We talk about the synthesis a couple of times. It's equivalent to a compile in software. In software, you write a C program and it will be compiled to an assembly program. And then assembly program will be changed to program code, which runs on a particular microcontroller, right? Synthesis is the same. The VHDL is synthesized to convert to a net list of fundamental cells. I already explained this. Fundamental cells, depending on a library and depending on a target platform, like the FPGA, ASIC, then the components which are available in your target platform will be used together, connected together to construct this functionality that you desire. Then there are several tools, including commercial and open source one as a synthesizer. There is a Synopsys design compiler and Cadence synthesis tools. They are the most common ASIC synthesizers, that they are used for fabricating the chip. And Usually the companies buy the license for them. For example, in universities, we have also, I mean, most of the universities or electrical engineering department or informatic means computer science department have the license for that, or one of them at least. But then there is a Xilinx ISE or ISE. ISE is a former version of the toolchain of Xilinx for the FPGAs. It's still working. I mean, you can still download it. It's not supported anymore. It stopped, I think, around 10 years ago. There is no update anymore, and this doesn't support the new FPGAs. But still, it's as a synthesizer, you may use it. But you keep in your mind the Xilinx synthesizers or Xilinx tools are just developed for FPGAs. Means that you cannot use them for ASIC designs. You cannot just ask them, okay, then synthesize my VHDL or Verilog code for an ASIC, one particular library like TSMC 45 nanometer. This doesn't work. Yeah, when they work only by synthesizing the code that you have for FPGA, like the lookup tables and switch matrices and so on. But of course, you can check whether the code that you have written is synthesizable. I mean, by ISE and also Vivado, and also you can check the functionality. Yeah, simulation you can do. But of course, the behavioral level simulation. I mean, a synthesis, if you want to target ASIC, then ISE and Vivado are probably not the best choice. And there is one open source, I mean, there are more open source tools, but one of them which is very famous and known is called Yosys. This is also open source. You can download it. It runs on Windows and also on Linux. This is based on ABC compiler or ABC synthesizer. And then they are all open source. I have to say that they work very well. They're pretty fast, but they are not well optimized. Yeah, it means that the code, the netlist that they generate, they are not necessarily the smallest netlist, because in hardware, the number of gates that you have or the latency of the circuit that you have are important. And then all these Synopsys and Cadence and the other companies that try to build the algorithms to make more efficient hardware. Otherwise, it's not hard to build a super large function that actually works and performs the operation that you want, but is super, super large. You know? This is not hard to do that. And Yosys, I wouldn't say that Yosys is bad, but Yosys is not meant for, let's say, optimization in latency and area. But of course, you can check whether it's synthesizable, and also the result of the Yosys you can simulate. These are the things that I think I explained already for you for Vivado. This is the snapshot of version which is not the current version. There is a more recent version of Vivado that you can download. As I said, there is a couple of gigabytes that you need to have to download it, and I recommend you to download it from probably your university network. Otherwise, at home, it may take an ages to download it and then install it. This is the Vivado, and I think I can show you one example here. Of course, we are not doing any synthesis or something like this. Here you can see that I have 3 different VHDL files. For example, function 1. Yeah, the entity again, the library, as I explained, is given here. Function of the entity is defined, and then ABCD input. This is exactly what you have seen in one of the slides. Yeah, we'll learn this later, and then you can run here synthesis. Yeah, run synthesis, and yeah, I have to say that the Vivado is not very fast. You may see it doesn't do anything, but you should wait. And you see here running synthesis design, and it's working now. And check whether, for example, your design is synthesizable or not. Yeah? What I would like to ask you before we go to the next or before the next session is to try to install a Vivado and make yourself familiar with the tool. In the next session, we will work more with Vivado, and some simulations and VHDL and so on. We will try to write some codes together and simulate it and check the functionality before we dive into, for example, cryptographic hardware. I mean, to implement really, for example, AES, which will be our first job, to implement AES in VHDL and simulate it and check their functionality. And then not next semester, not next session, but in 2 weeks, everybody who is still interested to continue the lecture should show up and then get the board, for the assignments. Because the first assignment, today you don't get any assignment. The assignment that I have for you is just make yourself familiar with Vivado and then install it and then try to play with it a bit. For example, get the license and install it and so on. Next week you get the first assignment. Means that today we don't have any assignment session. And then we will be done pretty soon. You see here the synthesis is done. Is the synthesis successfully completed? And then it asks me, what do you want to do? You want to run the implementation? Implementation means that we will learn this later, but the implementation means that the synthesized design should be now mapped to FPGA. I mean, it should not be configured inside the FPGA. There are different steps that we will learn later. Doing the synthesis, just turning the behavioral level description of your circuit to a net list of components which are available on the FPGA. In the next one, which is the implementation, it tries to put these components inside the FPGA, place them in the FPGA that you select, say, this is my FPGA, and it tries to see where it can put the components, like the lookup tables, and how it can configure the switch boxes, because the connection between the switch boxes are not arbitrarily possible. There are every incoming signal has some options to be connected to some outgoing signals. It means that every input connection is not possible to every output connection. Otherwise, the switching matrices would have been very complicated. And then the run implementation, it will try to just, as I said, find a place for them. And this is say, okay, this is mappable, I can map it, I can implement it. And the next level would be the generate a bit stream, exactly the bit stream of a single file that you need to put inside the FPGA to do exactly what you want to do. I mean, to realize this functionality. Okay, what was the question?
Just from experience from last semester, what are the hardware requirements for this program? Like memory, the amount of memory it takes?
Vivado usually is a bit memory hungry, I have to say. Number of CPUs that you have, it doesn't make much difference. I mean, it doesn't use many CPUs, at least in the free license version. But you don't need a server for that, particularly for the assignments that we have for the lecture. If you have a super large circuit that you build which doesn't fit easily inside the FPGA, then it takes very long time, because you should have, I mean, in general, there is a rule of thumb that 80% utilization you should have for the FPGA. It means that if your FPGA has 1,000 lookup tables, you should not use all the 1,000 lookup tables, because the mapping and the routing will not be possible, and it takes an ages for the tool to try to map, and it gives up after, let's say, a couple of days. And then, but for the examples that we have for this FPGA, they fit easily inside the chip, and it doesn't that long for the mapping. But I mean, you can see here, I mean, I can make a small error here without the semicolon, and you just save it, and it says synthesis out of date, and it means that I changed something and it's not synthesized. And then I can rerun the synthesis. And again, it takes a couple of minutes till it understands that, hey, I missed a semicolon here. I have to say that the ISE is faster, compared to Vivado. Did it start? Oh, yeah. I already canceled it. I think I have to run the synthesis again. Yeah. Okay, it's probably, yeah, run the synthesis, yeah. We will be able to also simulate the VHDL codes and Verilog, because I mean, it doesn't matter HDL or any HDL code you can simulate by Vivado as well. Again, I explained this already, that some VHDL codes can be simulated but cannot be synthesized. And this is not usually the case in Verilog. These are the things that I already explained. One example I have here for you, that there is an architecture that you say, hey, wait until blah blah, you know, this address request or adder request is 1, and then wait for 10 nanoseconds and then perform this operation. And this is inside a process. You can simulate it easily. Yeah? The simulator understands, because it's a test bench that you write. You want to assume that this is the, for example, you communicate with your call like this, but you cannot build the hardware out of this description. You know, to wait, for example, 10 nanoseconds and then wait for the address request to come. For that, you need to build something which has a clock, and the clock frequency is known, and you know how many clock cycles you wait, which is equivalent to 10 nanoseconds and so on. Yeah? This is just for simulation when you write the code like this. I think I already explained the goal is not to make you professional in VHDL. It just gives you or makes you familiar with the VHDL and being able to look at differences and references. I mean, differences to Verilog and any references that you want. I mean, if you want to write something, then you search for that, oh, how I can write if in VHDL, and then you find out the syntax, because what is it just difference? Our difference between Verilog and VHDL is just the syntax. Yeah? The concept is the same. And like in any other programming languages, it will be learned by doing. Yeah? I already explained this. You can find plenty of the books and the references for VHDL. These are the links. Let's see on Vivado again. You see successfully completed. I don't know how. No, it says syntax error. This is the reason. I can explain you here. Look. It finds out that the function 1 has a syntax error, and it puts it out of anything. Yeah, you see one of them is bold. This one, which is bold, is the top module. Now, if you have hierarchy, of course, for example, if the function 1 is instantiated inside the function 2, and the function 2 is the higher, then probably you should select the function 2 as a top module. Yeah, because the top module is there, and then function 1 is instantiated inside function 2. Now it realized that you have a syntax error, and it actually you are not able to probably make this set as top. You see this is off, you know, because it has a syntax error. It realized that, okay, you have a syntax error. And then when I synthesize, it actually synthesized x function 2, because this was the top module. You know? Now I bring it back. Now it understands, okay, everything is okay. Then I can make it as top. Yeah, and then I can synthesize, but I mean, syntax error, how I can, I mean, you should change it, check it by yourself when you have a syntax error. Of course, I mean, as I said, as an example, we have seen it cannot be synthesized, or Vivado pushes it out of the any option to synthesize it. No, but for example, I can put here x as input. I want to have it as output. It tries to update. Now it doesn't complain, but no, it complains here and say cannot update object x of the mode in. Yeah. And I can do again synthesize. I don't know what happens now. Yeah. And during this time, any questions? Yeah.
The in-out option, is it for debugging, like, or what is the purpose?
There are some modules that you can define in hardware generally as in and out by some selection bits, that they are in or out. For example, open collector signals. I mean, probably you're not aware of this. I mean, because it's too much electronics. But you can do it, but usually in simulation, in-out works easily, but in reality, in hardware, in FPGA, and also in ASIC, this needs another control signal to say this is which direction you have. Now, finally, you see a synthesis failed. It took a couple of minutes to understand that but as I said, I mean, you can see already this here. I mean, it already complains. I mean, from these things, Vivado is faster compared to ISE. ISE doesn't recognize this, that you just wrote here instead of out in. But synthesis is pretty slower compared, or at least slower to a start. Maybe the process of doing the synthesis is faster, but because the interface probably is a bit slower. Good. Any questions? No? Good. Then we see each other next week. And as I said, we will have the lecture plus the assignments, I mean, which is explaining the assignment to you. Because we don't have any assignment today, then there is no solving assignment in the next session.